Now we continue to learn Chapter 5, Orthogonality. Section 6, the Schimidt orthogonalization process. Part 2, this Schimidt orthogonalization process. A process for constructing an orthonormal basis for an n-dimensional inner product space V is called the Schimidt orthogonalization process. This method uses projections to transform an ordinary basis x1, x2 till xn into an orthonormal basis u1, u2 till un. First, we can define u1 by x1 divided by its length. It is clear that the span of u1 equals the span of x1 because u1 is just the direction of x1, the unit vector along the direction of x1. So of course, its span of u1 equals the span of x1. We then project x2 on to span of u1. We have this projection vector p1 equals this scalar times u1. The scalar is just the inner product of x2 and u1. Then, by the previous properties we learned in our previous part, so we know x2 minus p1 is orthogonal to u1. Define u2 as x2 minus p1 divided by its length. Then we know that span of u1, u2 contains in span of x1 and x2. Okay, because here you see u2 equals x2 minus p1. So p1 is a scalar times u1, where u1 comes from x1 divided by its length. So of course, x2 minus p1 is also a linear combination of x2 and x1. See? So clearly, span of u1, u2 contains in span of x1, x2. Since u1, u2 are linearly independent, we know that this vector u1 and this vector u2, they are orthogonal. Of course, they are linearly independent. Then u1, u2 is an orthonormal basis for span of x1, x2. That is the span of u1, u2 just equals the span of x1, x2. Okay. Now, to construct the next orthonormal basis u3, we continue in the same manner. Let P2 be the projection of the vector x3 onto span of u1, u2, which equals the span of x1, x2. So we write P2 as a linear combination of u1, u2. And the coefficient before u1, u2 is just the inner product of x3 and u1 and x3 and u2. So here P2, if we do like this, is a projection of x3 on the span of x1, x2. On the span of u1, u2, because u1, u2, span of u1, u2 equals span of x1, x2. And then we know that x3 minus p2, this new vector x3 minus p2 is orthogonal to span of x1, x2 to span of u1, u2. So next, we set u3 equals x3 minus p2 divided by its length. And we continue this process. So we have this theorem 5.6.1, the Schimidt process. Let x1, x2 till xn be a basis for the inner product space V. Let u1 equals xy divided by its length, and define u1, u2 till un recursively by uk plus 1 equals xk plus 1 minus pk, this new vector which is orthogonal to span of u1 till uk, divided by its length for k varies from 1, 2 till n minus 1, where pk is the projection vector, is a linear combination of the normal basis vectors u1, u2 till uk, and the scalar before those basis vector, also normal basis vectors, are xk plus 1 u1 do the inner product, xk plus 1 u2 do the inner product, till the last one is the inner product of xk plus 1 and uk. So this is a projection of xk plus 1 onto span of U1, U2 till UK. The set U1, U2 till UN is an orthonormal basis for this vector space V after you get UN. Okay. So proof. We will argue this by inductively, mathematical induction. Clearly, span of U1 equals the span of X1. Suppose that U1, U2 till UK have been constructed so that U1, U2 till UK is an orthonormal set, and the span of U1, U2 till UK equals the span of X1, X2 till Xk. Since Pk is a linear combination of the orthonormal basis vectors U1, U2 till UK, it follows that Pk belongs to this span of X1, X2 till Xk, and Sk plus 1 minus Pk belong to span of X1, X2 till Xk plus 1. And we consider this vector Xk plus 1 minus Pk, which equals Xk plus 1 minus summation Cixi for I varies from 1 to k. Since x1, x2 till xk plus 1 are linearly independent, it follows that xk plus 1 minus pk is non-zero, and by theorem 5.5.7, it is orthogonal to each ui. Since u1, u2 till uk plus 1 are linearly independent, they form a basis for span of x1, x2 till xk plus 1, and span of u1, u2 till uk plus 1 equals span of x1, x2 till xk plus 1. It follows by mathematical induction that u1, u2 till un is an orthonormal basis for this vector space V. So just find the span contained in this set, and it forms a basis for this span of x1, x2 till xk plus 1. Then you have this one. Now example. Here we consider an inner product on P3 on this functional space. This is also a vector space. Okay, find an orthonormal basis for P3 if the inner product on P3 is defined in this way. The inner product of two polynomials function P and Q equals the summation Pxi Qxi, where I varies from 1 to 3, where x1 equals minus 1, x2 equals 0, and x3 equals 1. Then how to consider this? So we first starting with the basis. This is a basis very easy to obtain, right? 1 x power 2, a basis for P3. But this basis is not orthonormal basis for P3 based on this definition of inner product. So we first calculate the length of the length of the first basis vector. So its power 2 equals the inner product 1, 1. The inner product 1, 1, because this is a constant function, so Pxi for each x1, x2, x3 is 1. So eventually this one equals 3, and u1 you will get is 1 over square root 3. Okay, so P1, the projection vector on span of u1 or span of x1 should be inner product of x and 1 over square root 3 times the first vector u1, 1 divided by square root 3. So this one, because this inner product x and 1 over square root 3, we seek its value from this formula. It's like Pxi, so it's minus 1, 0, 1, and here is a constant function, so the summation equals 0. So eventually you can find the P1 equals 0. Right? And therefore, x minus P1 length power 2 equals the inner product of x and x, and it's equals 2, right? So u2 equals this vector x minus P1 minus P1 minus 0, right? So it's just x divided by its length, square root 2. Finally, we calculate P2. So P2 is a projection of x power 2 on span of u1 and u2, u1 here and u2 here. Then we know P2 is a linear combination of u1 and u2, and its coefficients can be computed by just inner product of this new basis vector x power 2, and here do inner product with u1, here do the inner product of u2. Okay, and then you will find P2 equals 2 over 3. Then x2 minus P2, this vector which is orthogonal to span of u1 and u2. Its length power 2 equals this inner product, and substitute this inner product formula, we'll get it equals 2 over 3. So u3 is x power 2, this new basis vector, minus P2. P2 is 2 over 3 divided by its length. Its length is square root of 2 over 3. So eventually you will have this u3. So this constitutes an orthonormal basis for P3 with this inner product. So u1 is 1 over square root 3, u2 is x divided by square root 2, and u3 equals square root 6 over 2 times x power 2 minus 2 over 3. Okay, now we see this example. Let A be a 4 by 3 matrix. Find an orthonormal basis for the column space of A. Because column space of A contains all the linear combinations of the column vectors of A, so we consider each vector in A. Okay, in order to find the orthonormal basis, we just use this procedure, right? The first vector, column vector, divided by its length. Okay, so we found the column vectors of A are linearly independent and hence form a basis for a three-dimensional subspace of R4. We set R11 equals just the column 1, its length equals 2. Okay, square root of 1 power 2 plus 1 power 2 plus 1 power 2 plus 1 power 2 equals 2. And Q1 is a new basis vector, right? Orthonormal basis vector. The first one is just the first column vector A1 divided by its length. So it's equal this vector. Should be transpose, okay? A column vector 1 over 2, 1 over 2, 1 over 2, 2, 1 over 2. This is a column vector. And then we define R12. We compute R12, this constant, as the inner product of A2 and Q1. So in this vector space, we just consider its inner product as a transpose. So it's Q1 transpose A2. It equals 3. And P1 equals just R12 times Q1 equals 3Q1. So this P1 is a projection vector of A2 onto Q1. Okay, the first orthonormal basis vector. After you get P1, you use A2 minus P1. So this vector, this column vector, is orthogonal to span of Q1. And then you do this computation. You compute the length of A2 minus P1. The length of this vector is equals 5. Then the next orthonormal basis vector Q2 just equals this vector A2 minus P1 divided by its length divided by R22. So it's this vector, column vector. And then we compute other two values. One is R13. So R13 is the inner product of A3 and Q1. It equals Q1 transpose times A3 equals 2. And we compute R23, which equals A3, the column vector, and Q2 do the inner product, which equals Q2 transpose A3 equals minus 2. Then you can compute the projection vector of A3 onto span of Q1 and Q2. So P2 equals R13 Q1 plus R23 Q2 equals this column vector. Then A3 minus P2 A3 minus P2 is this vector, its length is this vector, then Q3, the third orthonormal basis vector, Q3 just equals this vector A3 minus P2 divided by its length, so it's equal to this vector. So the vectors Q1, Q2, Q3 form an orthonormal basis for range of A.